To make esters, you first need to have a carboxylic acid, which looks like this. C double bond O OH. And what you do is you add it to an alcohol. Just do an R prime OH. And going to be an equilibrium reaction so that you create your ester plus water. And what makes up the water is this OH from the carboxylic acid and this H from the alcohol. So essentially what you have is this guy, this lone pair on the oxygen attacking that carbon right there. And if you're not sure what the mechanism is, or depending on how deep you need to get, this is really essentially what you get. And that's a very brief synopsis of the mechanism, where you have a nucleophilic attack on this carbon here, this being the electrophilic carbon, because it's slightly positive and making the carbon a little bit reactive. Since the oxygen's electronegative, it's pulling the electron density of this double bond towards the oxygen. So you have this delta minus, this delta plus. And of course, electrons have some negative charge to it. There's going to be electron density surrounding this. Even though you don't see an outright charge, this alcohol can behave as a weak nucleophile because of these lone pairs, and it's going to go toward the delta plus. And again, the reason why these carbonyls are so important, you see them everywhere, is because it makes that carbon electrophilic reactive. Okay, so what you'll wind up with is, if you just connect the dots, well, you have this oxygen attached to this carbon here, and with the R prime trailing behind it. So you get this, right? This bond, this new bond being formed, and this guy, they both leave to form water. So that's essentially esterification, and it's a reaction that doesn't go to completion. It will come to an equilibrium, of course, meaning you have some reactants left over, and this happens in the presence of an acid catalyst, such as concentrated sulfuric acid, H2SO4. So let's I'll label that too. This is your carboxylic acid. This is your alcohol, and this is your ester. Yeah, in terms of these functional groups, you just kind of have to memorize them. If you can't remember, let's say, what the difference between an ester and a ketone, which is a common mistake, ketone has nothing to do with this reaction, but I'll just draw it to the side where you have R carbonyl group, then R prime. Well, an ester is just like ketone; it just contains an oxygen here. So you have OO, then R prime. You might think of it like if you have an ester that complains a lot, she's always saying OO all the time, complaining about this or that. So let's go into but we won't worry about that right now. We're not talking about ketones. So let's use the same colors. If I had something like a 1-carbon carboxylic acid, common name formic acid. Traditionally this is called formic acid. This could also be called methanoic acid. Yeah, a confusing part of chemistry is sometimes, even though you may learn the IUPAC names for things, the more traditional name is used more often. So that gets a little confusing, but it is what it is. So formic acid is a 1 carbon containing carboxylic acid. And then I'm adding to it something like isobutyl alcohol or isobutanol. And in the presence of an acid catalyst, something like concentrated H2SO4, I'm just going to combine the carboxylic acid with the isobutyl alcohol by removing water, the OH from this carboxylic acid group and the H from this alcohol group, and I'll just connect the dots. Remember that this is your nucleophile. It's going to connect to the electrophilic carbon, and if you do that, what you'll wind up with is instead of drawing the entire carboxylic acid over again, I'm going to draw not the oxygen that I had earlier, but I'm just going to draw the oxygen from here. Right. And then just continue along the chain, whatever the oxygen dragged behind it as it moved toward the electrophile. And there's my ester. Right. And my carbonyl, oxygen, and then some R group. In terms of naming the ester, actually the first part of the name would be the group that was originally part of the alcohol group. In naming an ester, the first part of the name is the group that was part of the alcohol group. So this is isobutyl. Right? And the rest of it is would be derived from the name of the carboxylic acid group, ending in ATE. So what I like to do is first write the group from the alcohol, or the name rather, or the root from the alcohol group, and then ATE, since all esters end in these 3 letters. And then what you need to do is think, well, what's the root of formic acid? And that's just this word, or these 4 letters here, form. So I have isobutylformate. Right. So what we can do, instead of just using an example of this general equation here, we can talk about the mechanism. This gets a little deeper, depending on the level of your course. You might not even need to know this, but let's see if we can draw it here. So if I would take the same reaction, and I'm going to draw the formic acid, and what the sulfuric acid is actually doing, if I draw it out, if I draw out the H2SO4, well, it's doing what an acid is supposed to do. By definition, an acid is a proton donor. So the lone pair, or one of the lone pairs on this oxygen, is going to move towards this H, the proton. Common mistake is having a proton move towards the electrons, and that never happens. Electrons are always the ones that are moving. Okay, even though this is kind of donating its proton, this is moving towards this. And then once it abstracts a proton, our pushing of electrons is going to go this way onto this oxygen. So what you have is positive charge on that oxygen, and you're left with kind of the anion of what was originally sulfuric acid, O minus, right, which lost its proton. So from there, I'm going to take this compound here. I'm just going to rewrite it. And what the acid does is it makes the carbon even more electrophilic. Here's how. This double bond, or these electrons that are part of this double bond, are going to move up here, and the positive charge is actually going to migrate to the carbon. And remember when we said the kind of the original electrophile of this reaction was what? Well, it's always 9 times out of 10 in organic chemistry, it's the carbon and the carbonyl group. And what makes it electrophilic is the fact that you have a nearby electronegative oxygen pulling the electron density towards the oxygen away from the carbon, making it slightly positive, or delta positive. Right? That's what we drew up here, right? But now, because of the acid that's present, there's an all-out positive, a whole positive charge on this carbon, one whole positive charge on that carbon. It's not just partially positive. So it makes carbon really reactive now. That's why it's an acid catalyst. And from there, what you'll get is, well, you'll get the alcohol, or I should say, one of the lone pairs on the oxygen of that alcohol, this being the isobutanol, moving towards the electrophile, so that I now have this here. Right? The alcohol is going to attach to that carbon, kind of dragging behind it its R group. It's going to be a positive charge on that oxygen now. And I could have just as easily drawn this hydrogen maybe on this side over here. And the reason why I'm getting at that is because what will happen at this step, is something called proton transfer. So what's happening is that this proton here is going to migrate towards, probably should have drawn on this side because you could then see how close it is to this OH here. But what will happen is, let's draw a dotted line. The lone pair on this oxygen is going to grab that proton. Okay, it's going to grab that proton. So what you wind up with is this. What you wind up with is H. Just going to redraw that H and OH. Nothing's happened to these guys. Now this becomes OH. Now it's got two H's with a positive charge on the oxygen since it grabbed the proton. And what was originally the alcohol group is now just O. The isobutyl group. All right. Since water is a good leaving group, and you have H2O after the proton transfer, water's going to leave. So you have minus H2O. And remember this from the beginning? From that very simple reaction, we had water. We had water as one of the products. Well, that's where it comes from. So if water leaves, these electrons are going to go there, and they have something that looks like this. Oops, almost forgot that isobutyl group there. And if the electron leaves, it's going to leave a positive charge on this carbon there. And in the final step, remember this guy that was formed when the acid catalyst donated its proton? Well, this guy's still floating around. Well, what will happen is I'll draw him in red now, I guess, since he's making a comeback over here. This is double bond O. This is the O minus is going to grab that proton there, and that negative charge is going to go down here. So what you wind up with is your final product.